class of power steering systems which are becoming very popular, particularly for passenger cars today, is what is called as electric power steering. Okay. So, as we can readily guess what the transition is, right, from hydraulic, electro-hydraulic, then we are going to pure electric. So, but as the name indicates, an electric motor directly provides the steering assist. Okay, so that is the feature of an electric power steering or an EPS. Okay. So, this is what is called as an on demand assist system. So, compared to the other two configurations, this has better characteristics in the sense that like the electric motor directly does the assist. So, the response characteristics are better, right. So, if you look at what is an on demand motor system, the motor or the assist energy, the assist is provided when the driver steers, and of course the motor can provide the assist depending on the design at various places. It can be closer to the steering wheel, like it can be towards the end of the steering column, okay. It can be on the rack, okay. So, depending on the designs there are various configurations, okay, as far as electric power steering is concerned. So, the assist is provided only when the driver steers, okay, and this also leads to lower fuel consumption. Why? Because compared to hydraulic power steering, where the energy is consumed in operating the motor pump continuously, right. So, this results in lower fuel consumption and consequently even reduced CO2 emissions, right, because fuel is saved, right. So, essentially these are positive benefits of electric power steering, and let us say it is more amenable to active control, right. So, essentially as we know, electric motors are more tractable for real time control. Even we can control hydraulic systems also in real time, but it is easier to build these controllers and program these controllers with an electric motor, right. So, essentially the power assist characteristics can be readily controlled, readily changed, controlled by appropriately programming the motor's ECU, right. So, that is a big advantage for an electric power steering. Okay. So, another advantage is that it can work even if the engine is stalled, as long as the motor has energy input to it, right. So, even when the engine is stalled, right. But what is the limitation? Please note that the motor requires energy to be operated. Now, if the size of the vehicle increases, the steering assist is more, then the motor rating increases, then the amount of energy which needs to be provided to the motor also has to be more. So, in a typical electric power steering, it will draw the energy from a battery and some which is interfaced with some intermediate power electronic circuits, right. Now, if we want a higher rating motor, the power density of the energy source should be higher, okay. So, but if we go with existing batteries, what will happen is that the rating of the energy source required to operate the motor itself will become higher, right. So, things are improving, but that is a limitation which we need to keep in mind, right, when we are trying to adopt electric power steering for heavier vehicles. Okay. So, one limitation is that the energy density for the motor power source, the pump, this is the assist motor, right. For the assist motor power source should be high enough to enable application in heavier vehicles. Okay, so that's one limitation of electric power steering. Okay, yeah, all right. So this essentially with this we have taken a broad overview of this type of steering systems and their configurations, their components, their operation, and also power assist systems. So the next task we are going to do, of course we have been doing some analysis as we are going along, but now we are going to analyze the steering response from a kinematics perspective. Okay. So let us do a simple first cut analysis. Essentially to analyze the kinematic response of the vehicle when it is steered. Okay. So for this purpose we will use what is called as a, to just start the process, we shall use what is called as a bicycle model, okay, for a car. Of course we are considering a 4-wheel vehicle. So in a bicycle model what happens is that the two front wheels are combined into one, okay, and the two rear wheels are combined into one. Okay. So a 4-wheel vehicle is viewed as a 2-wheel vehicle, and that is why it is called as a bicycle model. It is a reasonable model to start the analysis. Okay. So let us look at simple kinematics and see how one could analyze the response of the vehicle when it is steered by the steering systems that we have looked at. So what is this bicycle model? Let me explain, and we will also write down the assumptions and we will derive the equations. Okay. So this is just a simple schematic. So this kinematic the simple diagram schematic to essentially look at this bicycle model is as follows. Okay. So our vehicle is this line segment AB. So what we have done is that, like, we have combined both front wheels into one, both rear wheels into one, and then we are looking at the vehicle from the top. So and then observing what happens when the vehicle is steered, right. So that's our motivation. So please note that when we are looking at the so called bicycle model, we cannot capture the role of the vehicle body, because we have combined this two wheels into one and two front wheels into one and two rear wheels into one. This model can only capture the yaw motion or the rotation about the vertical axis, but as we know, when we take a turn, the body also rolls, the vehicle body rolls, right. So roll is nothing but rotation about the longitudinal axis, that cannot be captured by this model, but it is okay, it is reasonable to start off with. So what is this bicycle model? So this AB is the vehicle when looked from the top, and as we know, the wheelbase is capital L, and L1 and L2 indicate the longitudinal location of the CG from the front wheel and the rear wheel center. Okay. C indicates the center of gravity, right. So delta F and delta R are the steering angles of the front and the rear respectively. Okay. Without loss of generality, let us assume that both front wheels and rear wheels are steered. If you are steering only the front wheel, delta R becomes 0. Okay. So that is it, right. So that is a simplification. So we are deriving it for a general case, right. So, if only front wheels are steered, wherever we have delta r, substitute delta r as 0, that is it, right. So, only if only front wheels are steered. Okay. Now, this xy, capital X capital Y is an inertial frame of reference. So, the position of this center of gravity is given by a coordinate capital X capital Y, and this parameter psi, okay, is what is called as the heading angle or the yaw angle or the orientation angle of the vehicle. Okay. So, what is this psi? It is the angle made by the longitudinal axis of the vehicle with the capital X axis, the horizontal axis. Okay. That is the heading angle. Now, once again what we do? We draw perpendicular lines to the wheel plane, right, and that they intersect at this instantaneous center of turn, right. So, that is the instantaneous turn center. Okay. So, now if we draw a line segment to the center of gravity, capital R is nothing but the turning radius. Okay. So, now the velocity vector at the center of gravity is perpendicular to this line segment because it is rotating. Okay. We are neglecting what are called slip angles, we will come to that shortly. And then the velocity vector makes an angle beta. All these angles are exaggerated, by the way, like just to convey the concept, right. So, this beta is what is called as a vehicle side slip angle. So, it is the angle made by the velocity vector at the center of gravity with the longitudinal axis of the vehicle. Okay. That is what is called as beta. Okay. So, there are some interesting assumptions that are made when we look at the bicycle model. Okay. This bicycle kinematic model, okay. So, what we call as the kinematic bicycle model is reasonable, people have found out, is that like its accuracy is reasonable, okay, at low vehicle speeds. Let me put within what to say quotes. So, how much is low? Typically, like within, let us say 5 meters per second vehicle speed, this kinematic bicycle model is reasonable for road vehicles. Okay. So, it has been found that its accuracy is reasonable when you compare it with experimental results when the vehicle speed for road vehicles, right, is less than or equal to 5 meters per second. Okay. So, that is a reasonable model to use, and we neglect what is called as the slip angle at the wheel is neglected. So, what is this slip angle? So, typically when you go to a course on vehicle dynamics, you will look at it further. So, let us say we consider this pneumatic tire, and let us say this is the central wheel plane, and let us say this is the initial, this is the longitudinal axis of the vehicle. So, I am once again exaggerating. So, let us say this is the angle by which you steer the wheel. The velocity vector at this wheel center will not be along the wheel plane, okay. It will be at an angle to the wheel plane, okay. This angle which it makes with the central wheel plane is what is called as a slip angle, okay, and is very important, okay, in determining the vehicle dynamic response, particularly the conic response and even also longitudinal response, okay. So, we will see that this slip angle is very important, it affects the longitudinal traction, also more importantly the lateral traction, okay, which is available at the tire road interface. We are neglecting it here, okay. So that is an important assumption in this kinematic bicycle model. So if you look at this bicycle model, kinematic bicycle model from a big picture perspective, so if we draw it as a block diagram, we would immediately observe that the input to this model or the inputs to the model are the steering angles at the front and the rear. The outputs from the model are x, y and zeta, okay, because why? This x, y and zeta will characterize the state of the vehicle, right, at each and every instant of time, is it not? Because let us say someone gives us the coordinates of the CG with respect to the coordinate system and the orientation, we know where the vehicle is, also how it is oriented at each and every instant of time. That is why x, y, zeta will characterize the vehicle state at each and every instant of time, okay. So now we are going to derive the governing equations, okay. So the governing equations can be very easily written, but then like we will then go further and look at them, okay. So if you look at the governing equations, we need evolution equations for x, y and zeta, okay. So the evolution equation of x is given by x dot, and that is nothing but the x component of this velocity vector at the CG. What is that going to be? Assuming that the magnitude of the velocity is v, that is going to be v cos psi of t plus beta of t, is not it? Why psi of t plus beta of t? Because we have to consider this angle, right. So that is what will give me the x component, right. Then what will be y dot? Similarly it will be just v sin psi of t plus beta of t, right. Now what will be psi dot? You know, like we are neglecting these slip angles, we are considering the vehicle speed to be constant, that is another important assumption, okay. We consider v to be constant, okay, like the vehicle to go at a constant speed, right. So if it is going at a constant speed, we are taking a steady state turn. So this psi dot is nothing but angular speed, right. So it is going to be v by r, okay. So psi dot is going to be essentially v by r. In a transient maneuver it will not be, okay. So this is basically going at a constant speed along a path of constant radius, right. So essentially it is going to be v by r, right. So then these three equations form a set of governing equations, but however we cannot solve them right now, right, because we do not know what is beta, what is r, right. We need to get those values, right, because please note that the inputs are only delta f and delta r, the outputs are psi, x, y and zeta. So for this we are going to use simple geometry, that is it we are going to, right. So this is something which I am sure all of us can easily figure out. So if this angle is delta r, we already know why this is pi by 2 plus delta r, right, because this is the total angle. If this angle is pi by 2 plus delta r, how come this angle is beta minus delta r? That is because this angle will be now pi minus, right, pi by 2, correct, plus beta, right. So then if you use the sum of the three angles of a triangle is sum to pi radians or 180 degrees, you will immediately get that this angle is beta minus delta r. Similarly if you look at this angle, this is going to be delta of minus beta. Why? Because we already know this is pi by 2 minus delta f, that is pretty easy to figure out. This angle is once again pi by 2 plus beta, so this will be delta f minus beta, okay. So we can easily get that this angle is delta f minus beta, simple geometry, okay, nothing more than that. So once we have that, let us quickly derive the governing equations. So let us first consider triangle OAC, okay. I am sure all of us remember the sine rule. So sine of delta f minus beta divided by L1 is going to be equal to sine of pi by 2 minus delta f divided by R, right. Of course, I am not using the third ratio because that is not needed here, right. So that is what we get. So immediately we can quickly apply trigonometric identities. So this will become sin delta f cos beta minus cos delta f sin beta, that is going to be equal to L1 by R times cos delta f. From here what do we get? We will get, if we divide by cos delta f on cos delta f on both sides, we will get tan delta f cos beta minus sin beta is going to be equal to L1 by R, okay. So let me call this as equation 1, right, okay. Next what we do, we just go and consider triangle OBC. So if we consider triangle OBC and apply the sine rule once again, we are going to get sine of beta minus delta R divided by L2 is going to be equal to sine of pi by 2 plus delta R divided by capital R. So this will give us sine beta cos delta R minus cos beta sin delta R, that is going to be equal to L2 by R cos delta R. So what will this give us? If you divide by cos delta R, we are going to get sin beta minus cos beta tan delta R equals L2 by R, right. So let us call this as equation number 2. So we are almost through, so just 2 more steps. So now we can readily observe that if we add equations 1 and 2, what do we get? We get tan delta f cos beta, right, minus sin beta cancels off, cos beta tan delta R, that is going to be equal to L1 plus L2 by R. And what is L1 plus L2 by R? It is wheelbase, capital R. So this equation will give us an equation for the turning radius R. So L divided by cos beta times tan delta f minus tan delta R. So we have, as we discussed initially, we want to get equations for R and beta, right, if you want to solve equation 1. So we are not yet through, right, because even you can see that the equation for R depends on beta, right. So how do we get beta? One last step, that is it. So for getting the equation for beta, let us first multiply equation 1 with L2. So what do we get? So equation 1, if I multiply by L2, we are going to get L2 tan delta f cos beta minus L2 sin beta is going to be equal to L2 L1 by R. Then we multiply equation 2 with L1, right. We get L1 sin beta minus L1 cos beta tan delta R to be equal to L1 L2 by R. Now you can immediately see that the right hand sides are the same. So you subtract the 2 equations, right. What will we get? We will get, if you subtract, we will get cos beta, right. I am just writing the final equation. We will get cos beta times L2 tan delta f plus L1 tan delta R, right, minus L1 plus L2 sin beta equals 0, right. And what is L1 plus L2? This is nothing but capital L. So now we are almost through, right. So if we simplify, we are going to get an equation for beta. Tan beta is going to be consequently L2 tan delta f plus L1 tan delta R divided by capital L. Okay, so we are done. So we have got equations for R and beta. So do we get beta at each and every instant of time? Yes, we do, right, because delta f and delta R are the inputs. L1, L2, L we know, so we know beta. Once we know beta, we know R, and then we can substitute in the governing equation. So the final model per se will be the set 1, equation 3, equation 4, okay, and these equations can be solved to obtain the vehicle trajectory. Okay. So, this is the kinematic bicycle model, fine. Okay. So, we will stop here and then we will continue in the next class. Thank you.